At over 12,000 feet in the Khumbu region near Mount Everest, winter is not a season. It is a test. Temperatures fall below 40 degrees Fahrenheit. Oxygen levels drop by nearly 40% compared to sea level. Winds accelerate across open ridges, turning loose snow into horizontal blades of ice. Wood is scarce. Soil is frozen. Water freezes solid overnight. And yet, villages have stood here for centuries. The Sherpa people did not conquer the mountain with brute strength. They studied it. They observed how wind curves around ridge lines, how stone absorbs sunlight, how heat disappears the moment it touches thin air. Every house built here is not decoration. It is a response to physics. In thin air, convection behaves differently. Heat escapes faster. Moisture freezes inside walls. So survival demanded more than shelter. It demanded engineering. Before modern insulation, before thermodynamics textbooks, Sherpas built houses that conserved heat through mass, minimized wind exposure, and stabilized internal temperature using nothing but stone, timber, earth, and animal fuel. The question is not how they survived. The question is how they engineered permanence in a place that punishes weakness. Sherpa houses are not tall. They are compact, dense, grounded. Walls often measure 18 to 24 inches thick, not because stone is abundant, but because stone stores heat. This principle is known today as thermal mass. During the day, even weak Himalayan sunlight strikes dark stone surfaces. The stone absorbs radiant heat slowly. Because of its density, it releases that heat gradually through the night. In 40 degrees Fahrenheit conditions, insulation alone is not enough. We need delay. Stone delays heat loss. The thicker the wall, the longer it takes for interior warmth to escape. Sherpas selected flat metamorphic stone from nearby slopes. These stones fracture naturally into stackable forms, reducing gaps. No cement, just gravity and precision. The wall base is wider than the top. This lowers the center of mass, increasing lateral stability against high winds and minor seismic tremors common in the Himalayas. Small windows reduce heat loss. Doorways face away from prevailing winter winds. Every dimension serves a function. These houses are thermodynamic machines disguised as homes. Snow in the Himalayas does not fall lightly. It accumulates. A single cubic foot of compact snow can weigh over 20 pounds. Multiply that by an entire roof surface. Sherpa roofs are slightly angled but not steep. Too steep and wind rips the structure apart. Too flat and snow crushes it. The solution, moderate pitch with heavy timber beams running horizontally across stone walls. Timber is scarce, so each beam placement matters. Load transfers from roof, beam to stone wall, foundation, frozen earth. The system spreads weight evenly. Flat stones placed atop beams add compression weight, locking the structure downward, preventing wind uplift. It is a balance between gravity and resistance. In modern engineering terms, this is passive load distribution. But here, it is ancestral intuition refined through generations. Inside, survival depends on fire. At high altitude, oxygen scarcity reduces combustion efficiency. Fires burn weaker. Sherpas adapted. Central hearths are positioned strategically, often below ceiling vents, that allow minimal smoke escape while preserving heat. Fuel, dried yak dung. It burns slowly, steadily. Rooms are small by design. Less volume means less air to heat. Thick walls reduce infiltration. Sleeping platforms are elevated to avoid cold air pooling near floor level because cold air sinks. Even psychological warmth matters. Families gather close, minimizing emotional isolation during long winter months. Architecture becomes mental survival. Modern architecture often relies on machines, heating systems, insulation foam, imported materials. But Sherpa houses function without electricity. They use local stone, passive solar gain, thermal mass. In a world facing climate instability, perhaps the future is not always forward. Perhaps it is upward, toward lessons written in Himalayan stone. These homes were not built for aesthetics. They were built for survival, and they still stand. Building at sea level is labor. Building at 12,000 feet is survival. Oxygen is thin. Every lift feels heavier. Every breath costs energy. Stone blocks that weigh 50 kilograms feel like double. Workers must pace themselves. Overexertion at this altitude leads to dizziness, nausea, even collapse. Construction does not happen quickly here. It happens deliberately. Foundations must be laid into frozen ground. In winter, soil hardens like concrete. In spring, melting frost shifts surface layers. Sherpa builders learn to read the ground, testing firmness with wooden stakes, observing drainage patterns after snowmelt. Walls rise slowly. Stone is placed not just for fit, but for balance. Because once winter arrives, there is no repair season. You build correctly, or you rebuild next year. And rebuilding at this altitude is costly. So accuracy becomes survival. A single house can survive wind, but a village can defeat it. Sherpa settlements are rarely scattered randomly. They are clustered. Houses shield each other. Walls align with terrain contours. Buildings are often positioned behind natural ridges that break prevailing winter winds. Paths between houses are narrow, reducing open wind channels. This is passive wind engineering at a community scale. By placing structures strategically, wind velocity decreases before it ever reaches the walls. Even livestock enclosures are placed intentionally, acting as additional wind buffers. The village becomes a system, not individual buildings, but a collective defense. In modern cities, we rely on zoning codes. Here, the mountain dictates planning, and the Sherpas listen. Nothing is imported casually at high altitude. Every material carried upward costs energy, so Sherpa architecture is radically local. Stone from nearby slopes, timber from lower valleys, transported carefully. Yak dung from their own livestock, earth from beneath their feet. This reduces dependency, it reduces transportation risk, and it ensures material familiarity. Builders understand how their stone behaves in freeze-thaw cycles. They know which timber cracks under cold stress. There is no guesswork. Because materials are not foreign, they are native. In modern sustainability terms, this is zero carbon sourcing. But for Sherpas, it is simply practical wisdom. When architecture grows from its landscape, it belongs there. No written manuals, no engineering textbooks. Knowledge travels through observation. A child watches stone placement, learns which stones fit tightly, understands why the base must be wider, feels the warmth stored in walls, sees how snow accumulates differently on each roof slope. Architecture becomes memory. Mistakes are remembered. Success is repeated. Over generations, improvements are subtle but cumulative. A slightly better roof angle, a stronger beam joint, a more efficient hearth placement. This is evolutionary engineering, not through machines, but through memory. And because survival depends on it, the lessons endure. In extreme climates, tradition is not nostalgia, it is data. Emotional tone, proof, legacy, purpose demonstrate long-term durability. Ill voiceover, 3-4 min, storm after storm, winter after winter, seismic tremors that shake valleys. And still, many Sherpa stone houses stand for decades, some for over a century. The reason is not strength alone, it is adaptability. Stone walls can be repaired individually, beams can be replaced without dismantling entire structures. Roofs can be rebalanced. This modular resilience increases lifespan. Modern buildings often fail catastrophically. Sherpa houses fail gradually, and gradual failure is repairable. That is the secret of endurance, not perfection, but maintainability. And as the sun sets behind Himalayan peaks once again, these homes remain quiet, grounded, balanced, still standing beneath the shadow of Mount Everest.